Thanks to all the organizers for organizing this great workshop and for this opportunity to speak. Most of what I'm going to say today is joint work with Dan Nakano and Milan Yakimov. So let me start by just setting some notation. So in this talk, I'm always going to work over some algebraically closed field. Everything I assume is linear over K. Often K is going to be characteristic P, but always algebraically closed. T usually throughout this talk is going to denote some finite tensor category. So of course we have the standard assumptions. So tensor product is bilinear over K. All my Hom spaces are finite dimensional. Objects are all finite length. The unit object is simple. Finitely many simples, enough projectives, duals, all the things that we expect. So I'm going to get specific examples of monoidal triangulated categories coming from finite tensor categories, but some of the theorems I state will be for more general monoidal triangulated categories. And typically I'm going to denote that by K. So here it's a triangulated category, and we have a monoidal product, and this is compatible with the triangulated structure in a natural way. So I have to apologize for this assumption, of course. So none of my categories are going to be symmetric or even braided. So of course, maybe that's kind of inappropriate for this workshop. But the way that I want to frame it is I'm going to take methods from symmetric tensor categories and look at how they apply to more broadly to finite tensor categories, which don't have a braiding. So a lot of what I say will be things that are motivated by the theory of, for instance, finite group schemes or symmetric tensor categories. But we try to push it to this more general context. And I'll also assume that all categories in this talk are rigid. So we have left and right duals. Most of what I say, there's some version of it that would also be true if you left off duals, but I won't work in that generality. And yeah, and so like I said before, one will always denote the tensor unit. Okay, so we already saw some introduction to support in the previous talk, so I'm going to say several things in the next couple slides that are going to repeat some things that we saw, but let me say them again anyway. I'll probably say them in a little bit of a different way. So a support theory for me for a finite tensor category is just going to be some way of assigning a closed subset of some topological space, some geometric space for each object of the category. And of course, I don't want to just do this completely willy-nilly. I mean, I want to do it in some way that respects the homological and the tensor categorical properties of T. And there are going to be two major players for me that I'm interested in the relationship between them. One is the cohomological support, which I'll denote by W throughout this talk. And one is going to be the Balmer support, which I'll denote by V. So of course, we saw versions of these of both of these supports in the previous talk. And I'll say a little bit more about how we define both of these theories of support. But before I do that, let me move to the stable category, which again we also saw. And let me motivate it by saying, okay, one of the typical properties we want our support theory to satisfy is, well, projectivity detection. So we want our support theory to send an object to the empty set if and only if that object is projective. And in other words, another way of phrasing this is that our supports on our finite tensor category are well defined up to the stable category of T, which I'll denote in this talk by underlying T. And just to recall the construction of this stable category, so objects are exactly the same objects as we had in T. But now the Hom spaces, I take the Hom space in T, and I quotient out by all of those homomorphisms which factor through a projective object. So I kill all homomorphisms which go through a projective object. So in particular, every projective object in the original category becomes isomorphic to 0 in the stable category since the identity morphism factors through itself. And since I'm assuming that T is rigid, one can show that it's also Frobenius, which implies that the stable category is triangulated, and the tensor product is well defined in a way that's compatible with the triangulated structure. So here the triangles, the distinguished triangles in the stable category of T are really just the images of short exact sequences from the original category. And okay, so another way of saying this, right, I already kind of told you this before, that a monoidal triangulated category is just a triangulated category tensor product which is compatible with the triangles. So this stable category is one such example. And I'll kind of go back and forth throughout the talk. I mean, I'll say some things for stable categories, and then some things I'll say more generally for monoidal triangulated categories. I really think of this stable category as kind of the primary motivating example for these results. Okay, so let me say a little bit about our big picture. So to understand this stable category, or to understand the original finite tensor category, I mean, what would I want to do? Well, I might want to classify all indecomposable objects and understand how they tensor together. So in some sense, that tells me everything I want to know about the category. But of course, I mean, in even some very simple cases of finite groups, this is completely unreasonable. I mean, we have no way of classifying indecomposable objects, so of course no way of even starting to say how they tensor together. So a rougher goal we can replace with is to classify the thick ideals. So these are collections of objects I. It should be triangulated, it should be closed under direct summands, and it should be closed under arbitrary tensor products. So we can think of this as a rougher classification goal, rougher than just classifying all the indecomposables. And okay, so goal 2 is of course, like I said before, we have these two intrinsically defined supports, and I want to understand the relationship between them. Okay, so let me recall how we construct both of these support theories. So for the cohomological support, well, in any abelian category, we have a unita product that goes from between these X groups. And what does this do? I mean, of course, we can realize these elements of these X groups by extensions. So first an extension of A by B, extension of C by A. How do we combine these? I mean, of course, we just splice these two extensions together and get an I plus J length extension that starts at B and ends at C. And if we take, so here X bullet is just going to represent the direct sum of all the X I's of AA. And so using this unita product, of course, this X to AA becomes an associative algebra. And XAB is acted on by XAA and XBB on the right and left, respectively. Okay, so I have a module structure for each X to AB. And the cohomology ring, so I'll refer to the cohomology ring as X11. I get a ring homomorphism of X11 to each of these algebras X to AA. So how do I do this? I mean, we just use the fact that the tensor product is bi-exact. I can take an extension that starts at 1 and ends at 1 and just tensor the whole extension by A, and I get a ring homomorphism. Of course, there's nothing special about tensoring on the right by A. I could just as easily tensor on the left by A. But for the sake of defining support varieties, we can just pick one of these homomorphisms. So I guess I wanted to pick tensor on the right. I don't think that that'll actually play a role in the rest of the talk. But. So now we have an annihilator of X to A in the cohomology ring. So I'll denote this by I of A. And then cohomological support is just going to be the Zariski closed subset of proj of the cohomology ring, which is defined by this annihilator ideal. And of course, this originally was used by various people, Quillen, Dade, Carlson, Evrunen, Scott, Alper, and Evans, many other people. in modular representation theory of finite groups. So that's really where the motivation comes from. But we define it just as easily in the setting of finite tensor categories. So let me say a little bit more about thick ideals before I tell you our competing support theory, the Balmer support. So if we start with a monoidal triangulated category, then a thick ideal is just going to be some subcategory which, well, it has to be closed under the shift. It should be triangulated. So if we have a distinguished triangle with two elements of the triangle in the subcategory, then the third has to be in the subcategory as well. It's closed under direct summands. So we have a direct sum in I, then each of the summands are in I. And it's closed under tensor product with arbitrary objects. So of course, what else could we possibly mean when we say ideal? Right? And of course, I mean, just like an ideal is motivated in ring theory, well, it's the kernel of a ring homomorphism. Well, this is just really the kernel of an exact monoidal functor between triangulated categories. So what is the Balmer spectrum? So this was, of course, defined by Balmer in 2005. In this case, when I say commutative case, I mean for symmetric, or more generally for braided, and I'm going to use some natural non-commutative analogs of Balmer's definitions. So Balmer's spectrum is just going to be the collection of prime thick ideals. So this just means thick ideals P, such that it satisfies a prime ideal property on the level of thick ideals. So if I tensor two thick ideals together, and this is contained in P, then one of those thick ideals should be contained in P. And equivalently, I can also state the definition in terms of objects. So these are just thick ideals P, such that if A tensor K tensor B is contained in P, then A or B is contained in P. And of course, if K is commutative, so if it's braided or symmetric, then prime is just completely prime, which is just the usual prime property that we expect. So A tensor B in P implies that one of these two objects, A or B, is in P as well. Okay, so I guess here I wanted to say two guiding philosophies. So one is, okay, so when we write down the Balmer spectrum, we're really just copying down the spectrum of a ring and writing it down. So part of this philosophy is, okay, this suggests we treat a monoidal triangulated category like a ring. And the second is that categorical properties of K should be reflected or should reflect topological properties that happen in the spectrum. So this is a little bit vague, but I wanted to put it on the screen so that you'll remember this when I come to the main theorems. And really, if you told me at this point your time is up, you have to stop here, and I would say, okay, let me tell you the main theorems. The main theorems are, well, a monoidal triangulated category is like a ring, and categorical properties of K are reflected in topological properties of spec K, and that would be it. Okay, so I guess I told you what the Balmer spectrum was as a set, but let me tell you the Balmer support. So the topology is just generated by the supports of objects. So I should take in an object A of the category and give out a closed subset of the Balmer spectrum, and this is going to be those prime ideals such that A is not in P. So of course this looks a little bit backwards if you're taking inspiration from algebraic geometry, commutative algebra, but it turns out this is the one that we want. And so when I say generated by these closed sets, all I mean is a general closed set is just an arbitrary intersection of these. So it looks like we'll take some collection of objects S and then pick up all prime ideals which intersect that collection of objects trivially. And we have a related map, so I'll denote this typically in this talk by phi, or maybe phi sub v, which takes in a collection of objects and spits out the union of the supports of all of those objects. So this is what I'll mean, for instance, when I say the support of a thick ideal, what I mean is applying this phi sub v to the ideal. So the union of all the supports of all the objects in that ideal. And okay, so this, I guess I just want to note here that this gives a, well, not necessarily a closed set, because I'm going to be taking it on thick ideals, which have infinitely many objects. So it's an infinite union of closed subsets. So it's not necessarily closed, but it's specialization closed. So what's the use of the Balmer spectrum? Well, I already said one of our big goals is classifying thick ideals. And in many examples, determining the Balmer spectrum is the same thing as classifying thick ideals. And what I mean precisely is thick ideals are in bijection with the Thomason closed subsets of the Balmer spectrum. So what's a Thomason closed subset? So this just means a union of closed subsets such that each of those closed subsets has compact complement. Okay. And yeah, so I guess I'm going to tell you some examples in which this is true. So of course, this is one of the motivating theorems in Balmer's original paper. So if K is symmetric. It's also true if all prime ideals of K are completely prime. This is a theorem of Malik and Ray. It's also true as long as the Balmer spectrum is Noetherian. So this is a recent theorem of James Rowe. And then it's also true as long as K has a thick generator. So as long as there exists a single object K, or a single object A, such that the smallest thick subcategory of K containing A is the whole category. So for instance, it's true for stable categories of finite tensor categories, our favorite motivating example, because you take as the thick generator the direct sum of the simple objects. Okay. So of course, number 4 is what's going to be particularly useful for us if we care about this motivating example. So I guess I should say, so for finite tensor categories, I mean, of course, I want to consider ones which are not symmetric. So one wouldn't apply. We also know examples where all prime ideals are not completely prime. So we care about examples which don't satisfy number 2. Number 3, it's a conjecture. So it's a conjecture that the Balmer spectrum of this stable category is always Noetherian, but very hard to verify. I mean, or at least we don't know how to. But fortunately, we have this theorem in number 4, which says, okay, in this case, it doesn't matter. We still know that Thomason closed subsets of the Balmer spectrum still parameterize the thick ideals. And yeah, so I guess you can look at this list and say, okay, it's been known in the commutative case kind of forever. There's been kind of this recent flurry of examples in the non-commutative case. You might look at this and ask, well, I mean, could it be just true for all monoidal triangulated categories? And the answer is no. So we know in some joint work with Hongdi Huang, we produced some examples, of course, examples which by necessity don't satisfy any of these conditions. So examples with non-Noetherian Balmer spectra which don't have any thick generators, very non-commutative cases, where we know that Thomason closed subsets are not in bijection with the thick ideals.
Are these special particularly large chop-out design?
So the example you can do is take it's not so horrific. Take an action of the integers on a scheme, and then take the cross product category of dperf of the scheme, cross product with the integers, and you can come up with an example. Yeah. So not even that obscure. Yeah.
Is cohomology finally generated in that example?
I guess so. Yeah.
So in general, if you knew the Balmer spectrum would be Noetherian, you conclude that it's a non-clustered. Maybe you can talk about that.
Yeah. Maybe I have to think about that. Yeah. Good question. And so I should also say here, so like I said at the beginning, right, let me just remind you, we're assuming everything is rigid. If I wasn't assuming rigidity, you still have theorems of this form, but you have to replace, okay, you're not classifying the thick ideals, you're classifying the semi-prime ideals, or if you're in a commutative situation, you're classifying the radical ideals, right? So it's kind of like a Hilbert's-Null-Stellensatz type result where the radical ideals are in bijection with some closed subsets. But if we're assuming rigidity, every ideal is semi-prime, and I can just kind of give this kind of clean theorem. Okay, and let me tell you what this bijection looks like. So it's very easy to write down. If we start with an ideal, we just take it to the support of that ideal. It's the union of the supports of all the objects in the ideal. So that's this map up here. Or on the other hand, if we start with a Thomason closed subset of the Balmer spectrum, I just take it to the collection of objects whose support is contained in that object. And I should also say, so a fact that I'm going to probably be using throughout here is that this descends to a bijection between closed subsets. So if I replace this Thomason closed with just closed, and I guess I should say this is only if the Balmer spectrum is Noetherian, because then Balmer spectrum being Noetherian means every closed set is Thomason closed. But okay, under the Noetherian assumption, then this gives a bijection between principal ideals on this side and closed subsets of the Balmer spectrum on this side. So let me recall an example, maybe very quickly, since we've seen this just a few minutes ago. So we start with a scheme. We can take the perfect derived category. Then this is a commutative monoidal triangulated category, and it's a theorem of Thomason and Balmer that, okay, it recovers just the original scheme X. So in other words, we say that X can be reconstructed from its derived category. Or the other classic example, right, that Balmer includes in his paper is we have a finite group or a finite group scheme. So in this case, we have a third support player, which is the rank variety or the pi point variety. And in this case, again, all three of these supports coincide. So due to Everin and Scott, Friedlander, Pevsova, and due to kind of Benson, Carlson, Ricard, Friedlander, Pevsova, and Balmer. So Balmer just kind of put the thick ideal classification results into the kind of language of Balmer spectra. Okay. So why is this kind of such a fantastic theorem? So let me just say, so examples, so even for very simple examples, we can't classify the indecomposable objects. But like I said before, what we want to do is classify indecomposables up to some notion of equivalence. So we just want to classify them up to these kind of basic operations, and which is the same as classifying thick ideals. And this says, okay, you can classify modules up to this notion of equivalence. And it gives kind of a computational tool. So I pick up two random indecomposable modules, and I want to ask, does one generate the other by some finite sequence of these operations? Well, I just compute their support varieties. I mean, I just write down their cohomological support varieties, and if one is contained in the other, it means you can generate one from the other. Okay, so this is the kind of program that we're interested in trying to realize for general finite tensor categories. But when T is not braided, okay, we know cases where cohomological support and the Balmer support aren't the same thing. So the direct analog of the Friedlander-Pevsova theorem is not going to go through perfectly. So we try to repair it by considering some particular subalgebra of the cohomology ring. So let me define this as a categorical center. So it'll just be those elements of the cohomology ring G. So I kind of realize elements of X11. A homogeneous element should just be a homomorphism, a morphism in the triangulated category from 1 to some shift of 1. And I just require that this diagram commutes for all simple objects M. Okay, so here these are kind of standard structure isomorphisms in a monoidal triangulated category. Of course, these are just the unit isomorphisms. And I just require that this diagram commutes. And okay, once I have a subalgebra of the cohomology ring, I can just write down the definition of a support variety based on that subalgebra. So exactly the same as cohomological support from before, except now we take the Zariski closed subset in the proj of this categorical center instead of in proj of the cohomology ring. Okay, and it's some conjecture that we make that actually, okay, sorry, I copy-pasted this from another talk and said the conditions of the previous theorem, so just ignore that, please. So the conjecture is central cohomological support classifies the thick ideals of the stable category, and the proj of this categorical center is the same as the Balmer spectrum. So we know some examples. So of course, I mean, first I should say the examples that I just stated, right? These are examples where the categorical center is just the whole cohomology ring. Negron-Pevsova proved this for finite dimensional commutative Hopf algebras. We also know, kind of in general, for Benson-Witherspoon and for certain Plavnik-Witherspoon smash coproduct Hopf algebras. We also know for Drinfeld centers of these Benson-Witherspoon smash coproducts. And then in general, we have some examples that are joint with Hongdi Huang where we do some general cross-product categories. Okay, so we have some list of examples where we can verify the conjecture for. But there are some big obstacles to proving this conjecture in general. So let me say, what are the big obstacles? First is, of course, the Eddinghoff-Ostrich finite generation conjecture. So I think enough people in this room are probably familiar with this conjecture that I didn't feel like I need to write it down on this slide, but I can just say out loud. So of course, this is that for any finite tensor category, cohomology ring is finitely generated. And each of these X to AAs is finitely generated as a module over the cohomology ring. So, I mean, you'll notice in that conjecture, there's no mention of the categorical center. So what's the point? So the point is we can use this theorem of Negron-Plavnik to say that if we knew the Eddinghoff-Ostrich finite generation conjecture, then we could conclude that each of these X to AAs is finitely generated over this categorical center that we want to consider. And this finitely generated over the categorical center is the fact that we need.
So this conjecture implies that this central subalgebra is finitely generated as well?
Right, yes. I think that's true. That's true, yeah. We also need a kind of general version of the tensor product property. So I think we're going to hear more about the tensor product property later today. I want to use a kind of general version of this. So this is where we take a union over all objects B in the category, and I take the support of A tensor B tensor C. So maybe this is kind of bad notation. So here C is just an arbitrary object. It's not related to the categorical center. Probably I should have used D here, but then that would kind of have some aesthetic issues. But so I want this union of all of these supports to just be the intersection of the support of A with the support of C. And this is also, so of course the Eddinghoff-Ostrich finite generation conjecture is probably incredibly difficult to prove. This tensor product property, we also think it's very difficult to prove. And in many of the examples, I mean, it could be hard to prove even in simple examples. And even in the case of finite groups, it's a major theorem. And then the third major obstacle to proving our conjecture is that for kind of technical reasons, which I'll probably say a little bit more about, well, yeah, I guess I will say a little bit more about, we need to know that there's some kind of well-behaved extension of this support to the category of infinite dimensional modules.
What about these abstractions for symmetric categories? Again, more relevant for this conference. So maybe they're not as bad. So actually, I don't know. Eric is right saying that it's not clear that we should even believe our conjecture for general, even for Hopf algebras. But I kind of believe it much more for symmetric cases. And it's true, for example, for Verdier P to the n, as was shown in my paper with Benson. I suppose that part 2 would be greatly simplified in that case. And
yeah, I do expect. I mean, I think all of these, though, all of these are even difficult in the. I mean, they're major theorems in Benson, Carlson, Ricard for finite groups. So even for finite groups, none of these are trivial.
I think maybe one good point here would be like the supergroup case, where it's extraordinarily hard, and I think not much is known in that instance. So there's a lot, even in the super case. For the second point, the first point I don't know so much about, but yeah.
Yeah, my expectation is that things are probably easier for symmetric, but I think all of them are still non-trivial. So let me say, so we do have, under some weaker conditions, at least we can get a surjective map that goes in one direction. So this is under some weaker finite generation condition. So here, all I need to assume, I don't need to assume the full Eddinghoff-Ostrich conjecture. I just assume that each x day A is finitely generated as a module for this categorical center. So don't need to assume that the cohomology ring or this categorical center, either of them, I don't need to assume that they're finitely generated. Then at least we can produce a surjective map that goes in one direction. So a surjective map from the Balmer spectrum to the proj of this categorical center. And we can write down very explicitly what this map is. So it takes a prime thick ideal, and it gives out the homogeneous ideal of C bullet, which is generated by those elements whose cones are not in the prime ideal P. Okay, so here we don't need to assume, not only do we not need to assume the full power of the Eddinghoff-Ostrich conjecture, we also don't need any tensor product property or any extension. Okay, so let me recall this theorem. So I call this the Carlson connectedness theorem, which is if we have a finite tensor category, it satisfies the finite generation conjecture. Then if we start with an indecomposable object, then the cohomological support is connected. So this was proved by Carlson in 1984 in the case of finite groups. I love the title of this paper because it's very succinct. I think the title of the paper is something like the support or the variety of an indecomposable module is connected. And I love a title where it just tells you the main result. And then this was generalized by Berg, Plavnik, and Witherspoon to finite tensor categories. Okay. Yeah, of course, for Carlson, we knew that the modules of the finite group satisfied the finite generation property by these classical results of Golod, Vankov, and Evans. Okay, right, and it was generalized recently to all finite tensor categories. And yeah, and I should also mention here, there is a version of this theorem for triangulated categories. This is due to Buon, Krause, Snaschel, and Solberg. So also for a version of the cohomological support. I didn't include it in this theorem because you kind of have to require a number of technical conditions that I don't want to define or write down. But there is some other version of this. Okay, so let me summarize up to this point before I tell you our main results. So we've conjectured that for finite tensor categories, we have the Balmer support, and we have this central cohomological support, and we're conjecturing that they coincide. And okay, well, conjecture we think is hard to prove, but at least we get a surjective map in one direction. And we know from this Carlson theorem, or from the generalized Carlson theorem, that at least on the cohomological side, the support of an indecomposable module is connected. Okay, so our generalized Carlson theorem, we need a little bit technical condition, which is that our monoidal triangulated category okay, we need it to be generated by a single object. So of course, this was the condition that meant that Thomason closed subsets of the Balmer spectrum are in bijection with thick ideals. And of course, it's satisfied for our stable module categories. And I need this technical condition that it's the compact part of some compactly generated monoidal triangulated category. And that is true for the stable category of a finite tensor category. And I think I'll explain a little bit more of this setting in a minute, depending on how much time I have. But okay, then we just get exactly the version of Carlson's connectedness theorem, which is if we start with an indecomposable object in the category, then the Balmer support of this object is connected. So, right, so I just want to emphasize, right, these kind of technical conditions that we needed in order to connect the Balmer support with the cohomological support. I mean, we don't need any of these conditions. So we don't need any finite generation property. We don't need any tensor product property of cohomological support. And we also don't need, I guess I didn't write it, but we also don't need any extension of the support to the non-compact objects. So I think the remainder of the talk is kind of general how to prove this. And that's where the second part of my title, Generalized Chinese Remainder Theorem, is going to appear. Okay, so let me say a little bit more about this technical setting that we need. So an object is called compact. It just means Hom A blank commutes with all coproducts. So like we saw in the previous talk, this compactness is kind of like a smallness condition. Then I'm going to say that a general triangulated category is compactly generated. So here I'm denoting this by k hat. So this is, I think of this as kind of the big monoidal triangulated category, because one of the properties I want is that, well, there exist arbitrary set indexed coproducts. So this is, for instance, not going to include stable category of a finite tensor category, because, I mean, I don't have infinite coproducts in that. Okay, so I have to have arbitrary coproducts. I want the compact objects. I mean, of course, if I say it's compactly generated, what else could I mean except for this, which is that the compact objects generate the category under the operations of closing as a triangulated category and taking set indexed coproducts. And okay, so if I take a finite dimensional Hopf algebra H, I take the stable module category of H, well, this is the collection of compact objects in a compactly generated triangulated category, which is just the stable category of the category of arbitrary, possibly infinite dimensional modules for H. And okay, more generally, okay, also works for finite tensor categories. If I take the stable category of a finite tensor category, this sits as the compact part of the big category, which is, well, I take the indization of T, and then I take the stable category of that. I don't want to do, I mean, maybe the other direction, maybe there's something someone can say about the other order of these operations. So I could also ask, well, what if I try to take the indization of the stable category of T? But I don't quite know how to do this because of some pathological issues of triangulated categories. Maybe someone else knows how to do this. But if you do it in this order, you just take the indization at the level of abelian categories, then you take the stable category. You get a compactly generated triangulated category, which contains stable category of T as the compact part. Okay, so what's the point? I mean, of course, our theorem that we want to prove, this Carlson connectedness theorem, it's just a theorem about K. It doesn't involve K hat. So if I'm introducing K hat, we have to have some payoff for this technical condition. Well, let me set some notation. So loc I, here I'm going to have I, so I guess I should have said, so I should be a thick subcategory of the compact part K. So based on this, I can define loc I, which is just close I undertaking set indexed coproducts, shifts, and cones. So now we can use this result, Brown representability. So I guess this was originally named for Brown because it was originally a theorem in homotopy theory, but the general version in triangulated categories is due to Niemann. And what does this say? Well, it says we have these pairs of adjoint functors. So here, two of these functors, right? You should recognize immediately. So this is a subcategory of this. So this is just the inclusion of a subcategory. And then this is the Verdier quotient of k hat by this subcategory. So you invert all morphisms whose cone is in this subcategory. And so, of course, if you do a Verdier quotient, you get a standard functor that goes from k hat to k hat quotient. So what Brown representability says is that because these are compactly generated triangulated categories, we get adjoint functors which go in the other direction. Okay, so this is kind of the payoff for working in the world of compactly generated categories. If we did this at the level of k, we wouldn't have these functors that go back. And the two functors which we're going to build from these, so I just kind of compose the two pairs of adjoint functors. I get two functors that go from k hat to k hat. One of these I'll call Li. So Li is going to be the version which goes through the quotient. Gamma I is going to be the version which goes through the subcategory. And these are often called Ricard idempotent functors because they were used by Jeremy Ricard in the 90s during the during the classification of thick subcategories for a finite group. So let me note that, okay, this gamma I, since it factors through the subcategory, okay, it takes values in this localizing subcategory generated by I. And this Li takes values in the perpendicular space to loc I, so objects which admit no maps from objects in loc I. And for any object A, we get a standard distinguished triangle which goes from gamma IA to A to LIA. So you can kind of split an object A up into, in some sense, its part which lives in loc I and its part which lives in loc I perp. And this is a unique triangle, I mean, up to isomorphism. Okay, so let me say the Chinese remainder theorem. And okay, so I'm going to tell you a general Chinese remainder theorem for monoidal triangulated categories. But first, let me recall the classical Chinese remainder theorem, right? So what does the Chinese remainder theorem say? It says, okay, if you have a collection of pairwise coprime two-sided ideals of some ring R, then we get an isomorphism of R quotient by I to the product of the quotients by the R quotient by I sub i's. And here, yeah, I don't know if I said this. So here, of course, this just single I should be the intersection of all of the I sub i's. And coprime just means that together they generate the whole ring. Okay. Okay, so now what is a Chinese remainder theorem for monoidal triangulated categories mean? So here we want the same setup. So here K is going to be the compact part, I mean a small monoidal triangulated category, which is the compact part of some compactly generated monoidal triangulated category. And again, just like with the classical theorem, we have some collection of pairwise coprime ideals, except now we replace ideal with thick ideal. So then we exactly get what you might expect from looking at the Chinese remainder theorem. So if you take k hat and you quotient by the localizing category generated by the intersection of these thick ideals, you can write this as a direct sum of triangulated categories, which is the sum of the quotients of k hat by each of these localizing ideals. And if we look at the compact parts of these categories, we get some statement that looks similar using k quotient by the intersection, except because of kind of technical reasons, we need to take the idempotent completion of each of these categories. And the idempotent completion of triangulated category is triangulated, so this is a theorem of Balmer and Schlichting. And here, of course, just like in the previous slide, coprime just means that together they generate the whole category as a thick ideal. So let me sketch the proof. I think I have 6 more minutes. So let me do some quick proof sketches. So for the Chinese remainder theorem, the idea is just to use these Ricard idempotent functors. So here, if I and j are coprime, what one checks is that Li of one tensor Lj of 1 is just 0, which implies that Lj of A is the same thing as gamma I of A for all A in the category. And you can use this to show that we have the standard Ricard triangle for A, which goes gamma IA to LIA. And in fact, this triangle splits. So in other words, A is a direct sum of gamma IA with LIA. And here, gamma IA lives in loc I, Li of A lives in loc J. So this is how you get the decomposition for a pair of coprime ideals. So of course, we want to now induct and get an arbitrary collection of pairwise coprime ideals. And the point is, okay, if you have 3 ideals which are all pairwise coprime, then you can show that, that the intersection of I1 and I2 is still coprime to I3 using this kind of classic lemma. So here, what you do here is you take this version with I sub 1 and I sub 3, so that ideal is going to be the whole category. Here you take I2 and I3, so again the whole category, and then you just check that this one is going to be I1 intersect I2, I3. Right, and then of course you also have to check that, okay, as long as I is a thick ideal, then the big category quotient by loc I is the same thing as, oh, sorry, yeah, should be compact part. So compact part of the big category quotient by loc I is just the same thing as k quotient I, idempotent completion. Okay, so let me give also a quick proof sketch of the Carlson connectedness theorem given the Chinese remainder theorem. So here we use everywhere this theorem I said at the beginning that we can move back and forth between Thomason closed subsets of the Balmer spectrum and thick ideals of the category. So here we translate the condition that 2 ideals are coprime. Well, on the level of Balmer spectra, that just means that the supports of the ideals, well, their union is the whole spectrum. And the intersection of these 2 ideals is empty if and only if the supports of these 2 ideals are disjoint. And okay, so I think I'm lying a little bit here in that we use slightly more than just the decomposition theorem, but using kind of the proof of the decomposition theorem, what we can check is that if you have the support of an object, it breaks down into the supports of 2 other objects. So again, we're using here that all closed sets are in bijection with supports of objects. But then kind of using the proof of the decomposition theorem, it follows that A can be written as a direct sum of these, applying these Ricard idempotent functors to B and C in this category K hat. Okay, so let me say a little bit about some results that are recovered. So it recovers Carlson's original theorem. I mean, since the Balmer support corresponds to the cohomological support. It recovers a central cohomological analog of the Berg-Plavnik-Witherspoon theorem, as long as we have some conditions. So of course, in that case, still it's an open question of whether the cohomological support and Balmer support coincide. But under some conditions, we can deduce the connectedness result for cohomological support from the connectedness result for the Balmer spectra. So this, we need to know that, okay, we still need this generalized tensor product property, and then we also need this finite generation conjecture. And yeah, and I just wanted to emphasize here that these are weaker than the conditions in order to guarantee that they're literally the same. But okay, so under some weaker conditions, we can still deduce the connectedness result of one support from the connectedness result from the other support. And of course, special case is where we actually have the Balmer spectrum itself being written as a disjoint union of some closed sets. So in that case, well, we know that, well, there have to exist objects whose supports are these closed sets. And then we use the Chinese remainder theorem to decompose K into the product of these 2 triangulated categories. And I guess I wanted to note that, okay, the Balmer spectra of these categories well, the Balmer spectrum doesn't affect idempotent, or isn't impacted by idempotent completion. So spectrum of K mod I, idempotent completion is just the same as the spectrum of K mod I. And this is the same thing as just Z1. And likewise, the spectrum of this is just Z2. So this is saying that if your Balmer spectrum decomposes, then you can decompose the category, and it's compatible with taking Balmer spectra. Okay. Yeah, so I guess I'm out of time, so let me, I think these examples are not too exciting. So these are not really applications of the theorem, but are rather kind of proof of concept. So this one just says, if you have a disconnected scheme, then the derived category of the scheme breaks down as a decomposition of the derived categories of the two parts. And okay, and then I just note on this slide that this recovers some results of Carlson, Donovan Wheeler, Benson, Krause, who described particular quotient categories of a finite group, quotient by these particular ideals, which one can show that these two ideals are intersections of maximal ideals, which are of course maximal ideals are coprime. So this recovers some of these quotient decomposition results. Great, thank you.